All right, I'm going to continue with compound interest here with an example, and this example is to show you what happens when you start increasing the amount of compounding periods within a year. So let's suppose you invest $50,000 at an annual interest rate of 10% for a period of 30 years. How much would the investment be worth at the end of 30 years if the investment is compounded annually, semi-annually, quarterly, monthly, daily, or continuously? Now, we know that the following values aren't going to change here. The principal is going to be $50,000. The annual rate is 10%, 0.1 in decimal. And the number of years is going to be 30 years. So the only thing that's going to change is the number of compounding periods. So let's start with annual compounding. Well, with annual compounding, we know that M is 1 because that's the number of compounding periods per year with annual compounding, and T would be 30. So actually I would be 0.1 divided by 1, which would be 0.1. So that's a case where R and I would be the same when you have annual compounding. And N would be the same as T, because if you only have one compounding period per year for 30 years, then N would just be 30 years. So you'd have a total of 30 compounding periods. So if you apply the formula, if you apply this formula, then you would have the amount would equal the principal, which is $50,000, times 1 plus I, which is 0.1, raised to the 30th power. And you can check my calculations here, but I got $872,470.11. Now, that's not a bad return on this investment. But now let's do it with semi-annual compounding. Well, semi-annual compounding means you're compounding every 6 months. So that would be twice a year, and T would still be 30. So I would be 0.1 divided by 2. So your rate per period would now be 0.5 or 5%, 0.05 I mean, and 5%. And the total number of compounding periods now would be 60, because you'd have twice a year for 30 years. So you'd have 60 compounding periods. So change the I to 0.05 and change the N to 60, and now you get $933,959.29. So you got a significant increase in the total return by going from compounding once a year to twice a year. Well, what if we go to 4 times a year with quarterly compounding? Well, if we go to quarterly compounding, M would be 4. So that would mean I would now be 0.1 over 4, which is 0.025, and N would now be 4 times 30, which is 120 total compounding periods. So replace I with 0.025 and N with 120, and you get 967,000, almost 968,000. Well, you did get an increase, but notice the increase is not as significant as it was as when you went from once a year to twice a year. So, but you did get an increase. Okay, now what if you compound monthly? So M would be 12. Well, then you would have I would be 0.1 divided by 12, and I'm just going to leave that like that because it's not a terminating decimal. And you would have a total of 12 times 30, which would be 360 compounding periods. So let's replace I with 0.1 divided by 12 and replace N with 360. And now we get 991,869.97 So again, we got more money, but notice the amount, the increase is not as much as it was as from here to here. Okay, now finally, let's go to daily compounding. And if you do daily compounding, then that would mean M is 365. So I would be 0.1 divided by 365, and N would be 365 times 30, which is 10,950. So replace I with 0.1 over 365 and N with 10,950, and I get a little bit over $1 million here. Now, notice that the increase is not significant compared to the other increases. So it appears it seems to me like that as I increase the number of compounding periods, the return increases, the return on my money increases, but it seems to slow down as I add more and more compounding periods. Well, what if you could compound infinitely many times a year. So if you have trouble wrapping your head around infinitely, think about compounding every second in a year. And that's about as close to infinite as I can point you. All right, so actually calculus techniques can actually show that if you were to compound the money infinitely many times a year, then the amount formula comes out to be equal to this. It's the principal times the number E raised to the RT. So if we had money compounded continuously, if we had this $50,000 compounded continuously, then we would have 50,000 times E raised to the R, which is 0.1, times T, which would be the 30 years. And so 50,000 times E to this power would actually be $1,004,276.85. Okay. Now, don't expect to go to a bank and they tell you that they'll do continuous compounding, because most banks, the best you'll get is the daily compounding if you make an investment. But anyway, the continuous compounding is just a concept to show you that there is a limit to what an investment can grow to, regardless of the number of compounding periods you have within a year. So, you know, some of you may have thought this $50,000 could have grown to anything if I increased the compounding periods, but under these conditions, that's the most it could ever grow to, and that would only happen if somebody did allow continuous compounding. All right, let's look at it from a different vantage point. Let's ask this: how much should you deposit initially, so that would be the lump sum deposit, in an account that pays 10% compounded semi-annually in order to have $1 million in 30 years? Okay, so in this example, we know it's lump sum with compounding, but we want to know, now we're given the amount and we want the principal. So if you remember earlier, I may not have shown you this, but if you take the formula that I had for amount, remember amount was principal times 1 plus I to the n. If you solve that formula for P, you'll get P equals A divided by 1 plus I to the n power. Now another way to write that is that P is equal to A times 1 plus I to the negative n. Okay, that's just another way to write it. So now if we want to know what principal will grow to $1 million, we put $1 million in for my amount here, and then we take that. I'm going to use this formula first. So I'm going to put $1 million in for the amount, and then I, since we're compounding semi-annually, I would be 0.05, so I is going to be 0.05, and since we're compounding semi-annually for 30 years, then n would be 60, but since I'm using this formula for P, it would be raised to the negative n. So I'd have 1 million times 1 plus 0.05 raised to the negative n. So that means I would have to have a little over $53,000 in order for that to grow to $1 million in 30 years. And by the way, this is just another way to write it if you use the first formula where you do A over 1 plus I to the n. Now, what if we had monthly compounding? Well, if we had monthly compounding, the only difference would be is that the m would change to 12. So I'd have $1 million times 1 plus 0.1 divided by 12, and then the n would change to 360 because 12 times 30 would be 360. So I'd have this formula, $1 million times 1 plus 0.10 divided by 12 raised to the negative 360. So I would need $50,409 and change so that this would grow to $1 million at the end of 30 years if I had monthly compounding. And if I had daily compounding, just replace the m with 365, and then of course you know that 30 times 365 is 10,950. So I would only need $49,807 and some change for it to grow to $1 million if I had daily compounding. Well, again, I showed you this formula a minute ago. Okay, so that's the formula for amount if you know the principal, but if you wanted the principal, if you wanted the principal given the amount under continuous compounding, then the formula would look like this. So the principal would equal the amount divided by e to the RT. And remember, this is only if you have continuous compounding. So let's see if I had continuous compounding. Let's see how small I could make my investment so it would grow to $1 million. Well, let's put in the million up here for the numerator, and then the denominator would be e to the 0.1 times 30. And so there I would have e to the 0.130. So put that in the calculator, and I get $49,787.07. So that is the smallest amount that you could deposit that would grow to $1 million in 30 years. But that would only happen if you could get continuous compounding. And so I'll go ahead and stop the video here, and I'll do another video with just a random selection of problems from this compound interest section.